Okay, so thanks for coming to the fourth in this series of lectures. Yeah, thanks. So today I'm certainly going to talk about groups rather than topological spaces, and I'm going to talk more about algebra than topology. The groups I'm going to be dealing with are going to be significantly smaller than in just the preceding lecture by Gerhard Hiss. So I'm going to be interested in groups of order 32, 64. But just to give myself some credibility, let me write down a mildly bigger one. Let's take the third Conway group. And I'd like to say something about the cohomology of that group. And what I'd like to do is I'd like to have as an aim to give a formula for this group, which is true for all n greater than or equal to 0. So in lecture 2, I talked about the cohomology of groups, and I was talking about the second, or the third, or the fourth. So this is slightly different. And I'm going to make things easy for myself. I'm actually going to change the, I'm going to change the coefficients. So let's say z modulo 2. So that's really what I'm aiming at. And the computation involves basic linear algebra, like in the previous lecture, just Gaussian elimination, plus the multiplicative structure on the cohomology, which allows us to give, this is a vector space. So maybe I just want, for example, when I say description, maybe, for instance, its dimension. Like that. So that's maybe one of the aims. Let me give a formula for the dimension of the nth cohomology of that group. But I can't resist. I mean, most of my recent conferences that I've been to are all about applied topology. So I can't give a lecture these days without one picture from applied topology. That's the only picture from applied topology. So imagine that you have a collection of points, data points. I fabricated this on the computer. This picture is actually in 3 dimensions. So then you want to say, what kind of a manifold does it come from? So you do the business of Euthicke and you do your persistent homology. And let's suppose that you come up with some space that you think models it, X. And you say, fine, I've got X. So what can I say about X? Let's calculate its cohomology. And let's suppose that the space we found that models this data is two-dimensional. And let's suppose that it has it's connected, so the first thing should be the 0th cohomology is Z. The first cohomology is Z plus Z. The second cohomology is Z, and then it looks like it's come from a two-dimensional manifold. What manifold? Well, there are 2 obvious guesses. It might have come from the torus, because the torus has this homology. But equally well, if you take a sphere, a 2-sphere, and attach to it 2 circles, it has the same homology. So the homology won't capture everything about that space. So what I was talking about yesterday was really presentations of the fundamental group. And sure, you could use a presentation of the fundamental group and for this very simple example. But in all honesty, when you're dealing with presentations of the fundamental group and you use GAP, there is a constraint. Really, your presentation shouldn't have too many generators. It shouldn't be too big, otherwise, calculating Reidemeister-Schreier, presentations for subgroups wouldn't be practical. So we'd like to use homological algebra because homological algebra is the easiest kind of algebra that there is. It's the easiest topology. It's the weakest shadow of a topological space. So how can we do this using just Gaussian elimination? So we use the cup product. And let me just say what the cup product is about. So if I have a topological space X, I'm going to call delta the diagonal map. I take the direct product of X with itself. I take the diagonal map. So let's suppose in an example that I take X to be a circle. So I'm going to think of my circle as being something like this. Simplicial complex with vertices 1, 2, 3, 1. That's a circle. Now I'm going to take x cross x. So the best way I can picture that is maybe as a product of this with this. So it's the torus is x cross x. So I'm drawing the torus now, which is kind of 1, 2, 3, 1. I better get this right. A different copy. 4, 5, 1. And I say, well, let me draw the graph of this map. And the graph I'll draw in yellow just kind of wraps, it's a circle. You think it starts at 1, ends at 1, it's a circle. Right, so what I now want to do is I want to take the cellular chain complex on X. I want to take the cellular chain complex on X cross X. And I know from all of the topology textbooks at the beginning, they say that delta induces a chain map of chain complexes. But on a computer, there is something to work out. This yellow line, you see what happens? This one cell from 1 to 2 gets mapped here. It doesn't actually get mapped to a combination of 1 cells. It gets mapped, unfortunately, to the middle of a 2 cell. So there's a bit of a problem. How on a computer do you calculate delta star? So that's one thing I want to address. But let's for the moment suppose that you can calculate it. Then what happens? If you apply the functor Hom into Z or Z mod 2, you get each chain complex, Hom kind of reverses the direction arrow, so you actually get 2 co-chain complexes and a co-chain map going in the opposite direction. And then let's take n equal to p plus q for some strange reason. If you take the cohomology of these co-chain complexes in degree p plus q, you get a map on cohomology. But it's not too difficult to convince yourselves that if you take a cohomology class of degree p and a cohomology class of degree q, and you take their direct product, you get something which maps to 0, but it's of dimension p plus q, so you actually get a cohomology class, and so you get what's called the cup product. And the only issue in putting this on a computer is delta star. Apart from that, you just take the oldest topology book, Spania or something, and you just write down the formulae on the computer. Once you've got a cup product, and I think today I'm going to work over, well, no, I'm still over the integers. Yep, so I'm over the integers. This cup product gives you a graded commutative ring structure. So it's graded commutative means that if you take x times y, it's minus 1 to the pq y times x, where p and q are the degrees of x and y. But I'm going to work throughout the lecture p equal to 2, because it just simplifies a lot of things. Almost everything I say works for arbitrary p, so we can ignore the sign. So it's a commutative ring. And rather than rings, I'd rather work with algebras, so I'm going to change the coefficients just for that reason, and I'll work with field. So I'm not going to take spaces from applied topology. I'm going to take the following space. I'm going to take a group, maybe the Conway, the third Conway group, or maybe a group of order 32. I'm going to build a contractible space on which the group acts, e.g. I'm going to quotient e.g. by the action, and that's my space X. So the cohomology of BG is what I mean by the cohomology of the group. And if I want the first n degrees, at least as an abelian group, or even with the cup products, you only need to calculate n plus 1 terms of a free resolution. So if you can do that, you should be able to calculate that ring, at least in low degrees. Just to relate it to the applied topology example, in fact, if you take any space X, you can always take G to be the fundamental group. And then there's a map from X to BG, which on cohomology induces an arrow going the other way. So you always get a homomorphism that way. And in degree 0 and 1, this is actually an isomorphism on degree 0 and 1. So that does tell you some information about products, because this is an algebra homomorphism. It's a ring homomorphism. So if it tells you some information, if you want some information on this cohomology ring, well, a good place to start would be this cohomology ring. So that's some kind of motivation for why I'm looking at classifying space of groups. And then I've just changed the coefficients to make things simpler. F is the field of P elements throughout, but if I forget to say, quite often I'll be assuming P is 2. So how are we going to construct the diagonal map in this case? X is the quotient of EG by the action of G. Well, I'm going to do the following. I'm going to take my group G, and I'm going to look at the group homomorphism. G gets mapped to G cross G. That's a group homomorphism. And that group homomorphism induces a phi equivariant chain map of free resolutions. What I've written down here is a cellular chain complex of EG. So that's a free ZG resolution. This here is a free Z G cross G resolution. And they both have zeroth homology Z. So if I take the identity map from Z to Z and I say I want to construct a chain map which is phi equivariant, I simply map down here to Z, go to the identity, take some pre-image and on each generator and produce a map. I'm just using the fact that this is free. And I do the same. Once I've constructed this map, I take a generator here, I map down, a free generator, I map down, I go across. I know that if I go down here, it's the same as going down there, so I go to 0. Now I'm using the exactness of this sequence. There is something in the pre-image of where I am, and I can lift up to here. How do I lift? I'm repeating myself. I use the contracting homotopy that always I have to, one way or the other, I have to lift. And then you get a map of resolutions. And the thing that I want, the diagonal, is simply, well, I just kill the action of G, and I get my diagonal. So I mentioned the Cartan-Eilenberg formula. I wrote it down for homology the last time, so it's the same formula, but I've just written cohomology. And now I'm thinking of cohomology as being an algebra over this field. And the Cartan-Eilenberg double coset formula actually says a bit more than I said last time. It says that the thing that I'm interested in is a subalgebra so I'm taking the field of P elements. So if I'm working with the field of P elements, the thing that I'm interested in is a subalgebra of this, where the Zelo subgroup could be quite small. Which subalgebra? Well, it's very similar to what I wrote on the board the other day, but the other way around for cohomology. It consists of the stable elements, so you take double cosets and so on. So I won't go into that, but that motivates then looking at P groups. I want to start with a formula for this, so let me work up to that. So let me define the Hilbert series or Poincare series. So if I take my group G, and F is the field of P elements, let me define the polynomial P of T to be the sum of an Tn, where an is the dimension of the vector space, the nth homology of G. So when I write down this polynomial, all I have to, that polynomial gives me the dimensions of all of the homology groups that I want. So if I could write down that polynomial, I'd be done. There we have it. Okay, so this was a computer program, a computer calculation that Simon King, David Green, and myself did a few years back. So if you take the third Conway group, which is a nice example because the Zelo subgroup is not too big. I have actually forgotten. I think it's 2 to the 10. It's not too big anyway. So you're only looking at a group of size 2 to the 10. If you can calculate the cohomology ring, you can use Cartan-Eilenberg, and then what you find that the Poincare series is an infinite sum, and if you expand this out, you get the correct dimensions. So that is a formula for the dimensions that I'm interested in. And what's f of t? Well, it's a monic polynomial where those are the coefficients. So why do we do that? Personally, I do it because it's there. It's a mountain to climb, but there are other reasons. So, and how do we do it? Well, certainly we use the fact that this cohomology algebra is an algebra, and we use commutative algebra to do that. So, in fact, what you have to do is a bit more. You have to construct a finite presentation for the algebra. So what we do, I didn't write it down because there are 16 generators for this algebra and 71 relations, which wouldn't fit onto a slide because they're quite long. And the generators, they can be in different degrees. So the first generator, x1, is in the third cohomology group. And the highest degree generator lies in the, that's actually should be 15, so that's a mistake, is in the 15th degree cohomology group. And then the relations, they're actually words in this free algebra. They also have degrees. They're homogeneous. Sorry, they're not homogeneous, but the highest degree term on a relator is 33. So in order to get that, what we have to do is build 33 or maybe 34 degrees of a resolution. But how, to start with, you actually don't know how much of a resolution you need to build. Well, that's the problem. Now that I've told you the answer, you know that you only need 34 degrees of a resolution, but when you're starting, you have no idea how much you need. So just to kind of justify, this is not the reason that I did it, but I think it is probably the reason that Zeemon King was interested. He wanted to answer questions of Dave Benson. So Dave Benson had done some calculations and had suggested in a paper or conjectured that this cohomology ring should be Cohen-Macaulay, whatever that is. And so it turns out once you've got the ring presentation, you can actually verify using singular that it is Cohen-Macaulay. So what does Cohen-Macaulay mean? It means that the Krull dimension has to be equal to the depth, whatever the depth means, and they're both equal to 4. I won't get bogged down in the definitions, but you can answer questions. But I have a simpler example. Let's take the dihedral group of order 512. Okay, I'm using my notation. That's the dihedral group of order 512, and its cohomology ring, it's a bit easy to describe. It has this presentation on 3 generators, 1 relation, and the degrees of the generators are given there. And how do you, if you were interested in that, well, probably you'd look up a book on cohomology groups, but now you could actually just print into GAP the command mod 2, and here 2 is it's built into the command. Okay, so mod 3 won't work at the moment, but you type mod 2 cohomology ring presentation of the group you're interested in, and it churns out presentation. So what I want to talk about primarily is how does that one line of code work? What does it do? So let me just say something about mod 2. Cohomology rings. For small group, for G less than or equal to 32, they were all computed by Ruzin back in 1989. So presentations for all the generators, and also if I have time, I'll say something about Steenrod operations. Some Steenrod operations were also given there, but not all. Then John Carlson, Gerhard has mentioned this, started computing them. I think he started computing them in the late 90s, improved techniques. And it's really John Carlson's techniques that I'm going to talk about today, which are just linear algebra, which are now encoded in GAP as well. And for all of the groups of order 64, the cohomology rings are computed by John Carlson, but you can press a button in GAP and get them out. So it'll compute it on the fly. A student of David Green in 2011 computed a few more Steenrod operations for the groups of order 32, but there were still a couple of groups that were out of range of the technique. And one thing, if I get around to it, that I want to say today is that just by taking the oldest textbook on Steenrod operations and encoding the definition of the topologist, it works up for all the groups of order 32 and higher. So then, groups of order 128 in 2011, Simon King and David Green worked on those. There were two extra ingredients here. One of the ingredients was that David Green had developed some non-commutative Grobner basis techniques that work with finite P groups. So non-abelian Grobner bases were used there rather than the linear algebra that I'm going to talk about. And also, when you're starting a calculation, you don't know how many terms of the resolution you have to calculate, so you need some method for knowing when to stop. And the theory behind when you have to stop had improved by 2011, so that was also around. Okay, so as I've already mentioned, the computation has two parts. So what I'm going to talk about, I'll talk about these two parts. So it was shown back in the 60s by Len Evans and maybe other people like Benko that if you take a finite group, the cohomology algebra is a finitely presented algebra. So you know it's finitely presented. Which really tells you that if you want to do all of these calculations, your relations have a maximum degree. And you only need so much of a resolution to do the calculation. As I've mentioned, we don't have realistic bounds on the number of terms of the resolution we need. So what does that mean? Well, there are bounds in the literature on how many terms you might need. But if the bound is you need 256 degrees of a resolution, and your computer is fairly small and you can only struggle up to 40 degrees, the bound isn't very helpful because you'll never be able to achieve it on the computer. So I want to talk about that. And I'm not going to talk about the most efficient way of computing the realistic bounds. I think the most efficient way is implemented by Simon King in SAGE, and it uses a theory of Carlson on criteria for completion of cohomology ring calculations. But one of the things that I was kind of tempted in one of John Carlson's papers, he mentioned that Rusin by hand with the aid of a computer used ad hoc spectral sequence techniques. And clearly one wouldn't ever try to do this on the computer because they're so unwieldy and impractical. So I couldn't resist but write a paper using just the original spectral sequence technique to do the calculation. So I'm not saying it's as efficient as the more recent kind of theoretical bounds for completion, but it is the oldest method and it works rather nicely. So I want to calculate a free FG resolution, and I'm only really interested in the zero subgroup. So from now on, G is a finite P group. Well, for the moment, it's a P group anyway. I want to construct a resolution, and we can just work fairly naively, and you get quite far. So I'm going to take my first term to be the group algebra, FG. G is of order 32, 64, 128. So for me, that's just a vector space of dimension 32, 64, 128. It's not too big. We define the augmentation map, which just maps onto canonical map onto the field F. And then recursively, we do the following. So I've calculated the first part of the resolution, R0. Then recursively, we have a map of vector spaces. So I use Gaussian elimination, nothing else, to get echelon form, and I work out a kernel. As long as the dimension of the vector space is too big, that's quite fast. Then I somehow determine a subset of the kernel, not that generates the kernel as a vector space, but that generates it as an FG module. So I have to do that. And then what do I do? For each of my FG generators, I construct Rm+1 with one summand of the group algebra for each of the generators that I want to map onto. I just take that summand. And then I record what the boundary map is. It takes the ith summand to the corresponding generator in the kernel. And then, okay, I'm going to use the language of contracting homomorphisms, but that's a bit of overkill now, because in the first lectures I started off talking about the Klein-Bottle group, which was the group algebra is infinite dimensional, so you have to kind of be a little bit more careful. But here I'm talking of low dimensional vector spaces. So if I have a linear homomorphism, all I really want is a splitting. I want a map. The image, I want some non-equivariant splitting. Anyone will do up to Rn. So you can just use linear algebra to do that. And that's what I'll call my contracting homotopy in this case. So I'm not really using arrows, I'm just using linear algebra. But then there is this question, how do you efficiently, just by basic linear algebra, determine a subset of the kernel's FG span is equal to kernel? So then the radical, so if you have a module, a submodule of FG, actually if you have a sum end of a free, so let's say it's FG to the n. So I suppose I got the free, a direct sum of several copies of the group algebra. Let's take a module lying in that, is what I meant to say. Then let's define the radical to be, we know that. And standard theory really corresponds to the Frattini subgroup, tells you that the radical is an F span of those vectors. That's the definition, where F runs over a basis of M and G runs over a generating set. So, you've got lots of vectors to consider. And a basis for the quotient corresponds to a minimal generating set for the module. So you can actually find a minimal generating set for the module doing nothing but linear algebra. And you can build a resolution. And for the case of P groups over Z mod P, it happens that there is a unique minimal resolution. Minimal in the sense that no other resolution has fewer generators in each degree, and it's unique, and this algorithm produces it. So what determines the size of the computation? Well, certainly the order of the group, because I'm working in the vector space. I'm doing linear algebra in FG. So if G is large, it's not practical. But if G is only of order 6428, that's a fairly small vector space. The answer determines the size of the computation. If your answer is going to be big, well, the computation is going to be big. So here is a definition. Let's define the growth of G to be a measure of how quickly the dimension, I guess I probably mean cohomology there, but anyway, the dimension of the cohomology grows. In other words, let the growth be the smallest natural number, such that as n tends to infinity, the dimension of the nth degree cohomology divided by n to the s, the limit is 0. S is the smallest one. Call that the growth. And clearly, if the growth is big, it means that your cohomology, these vector spaces, are becoming big. And if they become big too quickly, working with summands, that's the nth term of the resolution. This will become a very big vector space if the growth is too big. So fortunately, we can say something about the growth. There's an old theorem of Quillen that says that the growth of the cohomology equals the rank of the largest elementary abelian P subgroup of G. Well, G is a finite P group. And the other thing that determines the size of the computation is again the answer. How many generators and what are their degrees? Because obviously if you've got a generator in degree n, you have to calculate n terms of a resolution. And if you have a relation in degree m, well, you clearly need n or n plus 1 terms. So the size of the answer depends, determines also the size of the computation. So, as I say, one method which I find satisfying because it's the original proof of finite generation of cohomology of finite groups, is just to use Dan Evans' proof that's very nicely written up in a book that Len Evans published just a year or so after he retired. I forget what it's called. It's probably called Cohomology of Groups, but it's explained very nicely, and you can just lift the explanation and put it into gap. It was so clear. I found that source. And I thought rather than run through the proof in general, I would just explain the proof in relation to one group. I'm going to take the group G of order 8. The quaternion group, sorry, G of order 8. So I hope I got this right. The quaternions, G, so I guess henceforth G will be Q8, it's an extension of Klein 4 group by the cyclic group of order 2, cyclic extension. So we've got that information. We've got this short exact sequence of groups. And in lecture 2, I talked about CTC Wall's resolution. And CTC Wall's resolution was designed just for this case of extensions of groups. So let's just recall CTC Wall's resolution. CTC Wall tells us in this case that we have a resolution for our quaternion group, which is a direct sum of modules dpq, where p plus q equal to n. So the degree 0 term is going to be this, the degree 1 term of the resolution is that plus that, the degree 2 term is that plus that plus that, and so on. And what is dpq? According to the construction I gave in lecture 2, it's just, well, find yourself a resolution for the group n, which we can do using linear algebra. Find yourself a resolution, I got this wrong, for the group Q, apologies, for the group Q, I'll correct this afterwards, and then you take the tensor product of resolutions. So take the tensor product of modules over Z of abelian groups, and that's what you put dpq. So from this data, this table picture here, you can do the following. Let me just define out of the blue EPQ0. Let's go back. Yeah, okay. So this here has an action on it. I haven't killed the action. This is tensored over Z. So now what I'm going to do, or over F. So here what I'm going to do is I'm going to kill the action, the G action on that module, and I'm going to call that EPQ0. So I get all these EPQ0s, and from the construction that I have on the computer, Wall's resolution, I've got all of these arrows that we've built on the computer. They're just the resolutions. They induce arrows on the E's, the E0s. And so the collection of all those arrows, shorthand, I'm just going to call D0, which goes from the direct sum of all the E's to the direct sum. Now I'm going to define E1 to be the homology of E0. That makes sense because D0 followed by D0, I'm just going twice down here, it's 0, they're chain complexes. So my E1 is the homology of E0, it's a direct sum under lots of abelian groups. And I also get homomorphisms of abelian groups going horizontally. So where do they come from? Well, in my Wall's resolution, I've got lots of horizontal homomorphisms, which I've called D1s. All of the horizontal ones are called D1s. They induce a morphism. So, and then what do? Well, we take E2 to be the homology of E1. All of those horizontals they square to 0, so I can take their homology, and I get E2. And not only that, I get homomorphisms D2, which go from here to here. But these are actually on the computer because the resolution we're using is this one from CTC Wall, which, as part of the boundary, has maps that induce the things I want. Okay, so I could go on and on and on. You could imagine E3, E4, but I'm only working with groups. So then the next ingredient is cohomology is algebra, and the algebra structure transfers to a multiplication in this setting. In fact, the Lyndon-Hochschild-Serre spectral sequence is what I'm talking about, tells us that this E2 term can be thought of as an algebra, and it can be thought of as this algebra. This is, in our example, the cohomology ring or the cohomology algebra for the Klein 4 group, tensored with this algebra, the cohomology of the cyclic group. So I can write those down just from hand calculations. I know what they are. But what the computer gives me, if I chase everything through, is homomorphisms from all of these summands. I get this homomorphism, and that homomorphism is a derivation. So d of x, y plus, I don't know, y d of x, or however you write it. It's a derivation. Sorry? I'm over F2. Yeah, but in this case, I'm working over F2. It's a derivation. And because I'm working over F2, things are actually quite nice. If I do d of x squared, I guess I get 2 times something, which is 0. So any squares go to 0. In fact, if I do x plus y squared, it goes to 0. So if I were to work, if I were to take, I mean, so what the next line I want is what this is the Lyndon-Hochschild-Serre spectral sequence, yeah. But I just want to explain. Yeah, okay, well, okay, I guess so you could go on, in general, you take in theory, you take the nth page to be the homology of the n minus first page, and you keep track of all these arrows, so you have this on generators as a derivation on the computer. Yeah? So now, this is the bit that I should say something about. I'm not going to talk about Grosvenor bases. There is something which I'm not expert in. They're implemented in many places. In particular, they're implemented in singular, and singular links very nicely to gap. And for commutative rings, Grosvenor bases are implemented efficiently in singular. And for Grosvenor bases, you can do things like you can find the kernel of a ring homomorphism, which is a bit of an issue, because this isn't a ring homomorphism. But it is actually a module homomorphism. If you take inside E, if you take the subring generated by all squareds of generators, x2 squared and so on, E is actually a finite dimensional module over this, and you can use Grosvenor bases to find the kernel of a module homomorphism. So because I'm working over the field of 2 elements, I can actually use Grosvenor bases. And in fact, if I'm working over the field of p elements, the same trick goes through. But there is an issue. With p elements, I have to remember that the cohomology ring is graded commutative, so I have to be careful when I'm using Grosvenor bases for commutative algebra. So, but they are also implemented in singular, but we decided to focus on the I and p equal to 2. So that's really the only place where I'm using p equal to 2 for the practical reason that there was a postdoc who spent 3 years working on this, and to make life comfortable, we said, let's just take p equal to 2. So then at some stage, this converges. The nth page becomes isomorphic to the n plus first page, and standard or easy commutative algebra tells you that if you want generators and relations for this thing here, this spectral sequence converges to this. So that doesn't mean that it's equal to it. It means that up to extensions and so on, they're equal. But it's not too difficult to see that the the minimal degrees of generators and relations for this thing that you can calculate coincide with the minimal degrees of generators and relations for the thing you want to. So for the case of the quaternion group, you run it on the computer using singular at each stage to calculate kernels and images, and you find that it collapses at fourth term, and therefore that E infinity or E4 is a ring with presentation with generators and relators of degree less than or equal to 4. So now I want to go back to my group and I say, well, okay, I only need 5 terms of a resolution. I build my 5 terms of a resolution, I find all of the generators and relations that there are, I'm done. And that's what's going on in the gap command onto homology ring. And so I have 9 minutes, which is fine, to say something about Steenrod operations. So the message I'm probably getting boring people, I keep saying once you've got these contrasting homotopy, you can do everything in the books. So Steenrod operations seem to have been a problem for a number of authors because they couldn't finish the calculations on the groups of order 32. So what is a Steenrod operation? Well, it's a for each I, there's something called a Steenrod square, and it's a homomorphism from this group or this vector space to that vector space. For I equal to 0, it's just the identity homomorphism. For I equal to 1, it actually coincides with the Box-Stein spectral sequence. So if you have a short exact sequence of abelian groups, that induces an exact sequence in cohomology. Around. Oh no, this is yeah. So Z2, it goes the same direction, doesn't it? Yeah. And so on. So what does it tell me then? So I get a homomorphism. Some things the wrong way around, haven't I? It should be decreasing. Yeah, thank you. Yeah, I always think in terms of homology. So so now I change all my arrows. So I get a homomorphism. Oh no, I did 2 corrections, didn't I? Okay. Yeah, I did 2 corrections. That's 1 correction. So I get the homomorphism. And it turns out the theory that square 1 is that. Why is it SQ? Why am I talking about squares? If x is in degree I, then the square of x, or the square I of x is just x squared. So when x is in degree I, it really is a square. And I actually have the cup product implemented, so I can calculate it in degree I. When I is if x is of degree less than I, then the square is 0. Squares are nice, they're additive. And this is a very useful relation on the computer. The square I of a product can be written as the sum of squares of other squares. So you can do things recursively, and you don't have to calculate the square in every element. These relations tell you that, in fact, you only need a handful of elements, that you have to specify what the various squares are, and then you have the whole action of the Steenrod algebra. That one isn't important for what I have to say. And then this is the Adam relation, which I should actually implement in GAP because that would speed things up further. I'm not using the add-in relation at all. So the current GAP implementation ignores this lovely piece of mathematics. Could speed things up. So what you can do in GAP is you can take a group. I'm not saying it works for all of the groups of order 64. It certainly works for all the groups of order 32. I've taken the dihedral group. You have to decide how many terms of a resolution. This one isn't intelligent. You have to tell it how many terms of a resolution are you going to use. So as long as you give it enough terms, which you can work out because you can first of all calculate the cohomology ring. It says how many terms of the resolution you need. And then what it does is it prints out some gap information, the order of the group number, the group description, the cohomology generators. So it says that this cohomology ring has 2 generators in degree 1 and 1 generator in degree 2. The relations for the cohomology, the Poincare series, which I defined, and the Steenrod squares, and in this case, which actually does fit onto one slide, the only Steenrod square you have to specify is square 1 of C, and it turns out to be C times A. I have 3 minutes left, so as usual, I flick very quickly through my last 2 slides. But that's fine. Let me just say something about the classical construction of the Steenrod squares. They're based on the cyclic group of order 2. So G is my group I'm interested in, but I've always got the cyclic group of order 2 generated by Z. G is the group I'm interested in, so I have to build a resolution for G cross G, which I actually showed on an earlier slide. I have to build a resolution for G cross G. And C2 cross G is also a group, so somehow I have to build a resolution for C2 cross G. Now these resolutions, I put over Z, but in fact, it suffices to work Z mod 2, so I can actually construct minimal resolutions for these. C2 cross G acts on these modules by a formula which is in all the books, which is given there. So it's something that can be implemented. So there's a formula, there's an action of this group on each of these modules. So these are G cross G modules, but there's this action. And this is the bit in blue, the only bit that I really want to talk about on this slide. Because you've got contracting homotopies on this free G cross G resolution. Well, actually, no. Because you've got, this is a free C2 cross G resolution. This is free. This, I'm going to forget that it's a G cross G resolution. I have an action. So it's a non-free C2 cross G resolution. So I have a free resolution of C2 cross G and a non-free one of C2 cross G. But over the identity, I can use this action to induce a homomorphism, which extends this in degree 0, and I construct that phi star. So then each of my free modules, that should actually be, in our case, F. I take Hom, and so there's a way of associating a generator here to the canonical dual, Hom. And then there's a formula that you can read at your leisure. The only thing I want to say is that the formula involves phi. So in order to implement this, you need to implement phi, which in blue, I'll explain how to do it. It's just contracting homotopies. And then the final slide, I got there today, 1 minute ago. The final slide says that the Steenrod squares that I was talking about are constructed in terms of something called SQn-1, where what's SQn-1? Well, it's an operation. This operation here, whatever it is, induces something called SQn-1, and then when you change